Hello, and welcome to the third episode of our introduction to SDN. By this time, you probably have had enough of our theory crafting, and it is good because this time we are starting with a more practical discussion, OpenFlow protocol itself. Being a protocol, OpenFlow defines a set of messages for all the communicating parties to use and their contents. So basically, it's a document. It's a spec not only for messages, but also for a switch to conform to OpenFlow standard to be a proper remote control plane client. It defines that a switch has to only care about a proper management channel to the controller, have a port manager subroutine so that port state is properly reflected in software and later in messages to the controller, and finally to care about and to maintain the flow table. Protocol itself is a binary protocol with a strictly defined set of messages and their contents. It operates over a TLS encrypted channel, and the standard port for it is TCP 6633. The basic OpenFlow function is to consult with the controller on what switch has to do with every incoming packet. It's counterproductive, obviously, to do that for every packet in a stream. So usually the controller installs a rule or rules to be applied on them, instead of asking the controller again. Rules themselves are contained in the switch flow table, and Spec defines the flow table as just a table of flow entries which are match and action pairs, where matches are regular ACL style or firewall style entries that try to match the given frame or packet against a fixed set of fields and their entries. This table leverages the TCAM hardware, and in that it can allow you to omit or wildcard some of those fields so that you match only against fields you are interested in. It is probably the right time to say that we will start with discussion of OpenFlow 1.0 as the most basic protocol. And in 1.0, we have only 12 kinds of fields to match against. Actions, one or multiple, are attached to any given entry, and they define what to do with a flow that conforms to a given match. There can be as many entries as you want, or in more practical terms, as many as switch hardware allows you to. And these entries are checked in a top-down manner, very much like a traditional firewall policy list. If there are no actions provided for any given match line, default action will be drop. And to add to that, every table, flow, port, or any other element of a data structure can contain counters per byte or per packet, although this feature is optional. Among many OpenFlow features and properties, lots of them are marked as optional. So please be advised, if you buy an OpenFlow conforming switch, you have to carefully check what actions and what messages and what counters are actually supported. Such an optional feature is, for example, queuing. So what actions are out there? Well, the most important is forward action. We can define a forward destination as all for any flow to be multiplied and sent out to all ports except of the incoming one. Or be it a controller destination, local destination to a local switch network stack. For example, if this switch is a Linux-based machine, we can actually communicate with the Linux operating system this way. And of course, there is send to some port number not shown here. You can see that normal destination as well as flood are marked as optional. That is because normal naturally requires for switch to have some sort of an inbuilt control plane, traditional or legacy path for flows to be processed. And flood, again, requires for switch to support STP protocol and all the required messages and state handling inside. These types of destinations are a good example how not all OpenFlow features are actually available in every device. Among other important actions are modify field and Enqueue. It is quite clear what Enqueue does, but modify field is a very powerful tool that, again, unfortunately is a completely optional feature that allows you for a given match to change any packet header entry, be it an IP address or MAC or VLAN header. And actually, this feature is among most popular one of OpenFlow protocol. Just imagine your switch without any modify field functions. What can you do? You can just match a packet and send it out of the port. Well, that is not too different from a traditional switching. Experimenters quite often want to see ability to add or pop VLAN tags, modify QoS tags, and so on and so forth. Let's check again the code snippet we've seen in the previous episode. This time it is much clearer what sendFlowModAdd function does. It sends a message from the controller to switch. And we can see data path ID, that is a switch identifier provided, with match structure and actions list to be entered in the flow table. In the future OpenFlow versions, actions are actually wrapped in an instruction structure, basically making actions a subset of all possible instructions, and the instructions supporting things like switching between different flow tables. So sendFlowModAdd sends a message. What messages are here? Well, the spec defines three kinds of messages, which are controller to switch, with response or not, but initiated by the controller, asynchronous messages that are sent by switch without controller request beforehand, and symmetric messages that can be initiated by any party in the OpenFlow communication and require some sort of a response. Controller to switch messages contain the obviously most important one, modify state, and we've seen sendFlowModAdd in the previous slide, which is a subset of modify state message, among other like modify strict or delete strict. All these messages have to contain some sort of a match and optionally an action list. Among other often used messages of a controller to switch type is a features request and feature reply and send packet out one. Unlike modify state message, send packet message does not provide a match structure. Instead, it provides a completely built, ready to be sent out frame, so the switch just serializes it from one of its ports. Basically, it's a way for a control plane, while being remote, still be able to send any information, be it STP or SPF or any other kind of packet, out of any given switch port. The asynchronous set of messages contain the packet in one, which is actually the message that will contain a packet that got no matches in the flow table of the switch. So basically, the functionality of OpenFlow is to allow switches to ask the controller, what should I do with this packet and the subsequent packets with the same header? And for the controller to reply with the rule that will be installed to the flow table. Other asynchronous messages are also quite important. The flow removed one will be sent to the controller by switch if, for a given match, there is a notify on remove flag set. Port status is a message that is sent by switch on every port state change, for example, port going up or port going down. And naturally, there is a possibility to report an error. And finally, symmetric, the most trivial set of messages, is just a set of hellos to initiate an OpenFlow connection and echo request and echo reply for a heartbeat between a switch and a controller. Heartbeat is here, so the switch always knows if controller becomes disconnected. On a controller loss, the device switches to an emergency mode. In emergency mode, only flows that are flagged as emergency flows will remain in the flow table. All other entries will be deleted, and hopefully our network functionality will degrade in some sort of a controlled way. So that is the essence of OpenFlow. There is quite a lot of other features and entries and messages that you can always read about in the OpenFlow spec, but the core of its functionality is given. Switches connect to the controller over a regular IP connection from the management port. Switches communicate their features and expect the controller to manage the flow table in future. Whenever a new packet comes to a port, there is an attempt to match this packet against the flow table, and if there is a match, there will be an action set to perform on this flow. And finally, if no matches are in the table, there will be a packet in message sent to the controller to make a decision. But OpenFlow also progresses and progresses rapidly. In the subsequent to the initial release years, it became apparent that OpenFlow in its bare bones 1.0 version actually isn't that ready to a real production use. For example, in 1.0, if you wanted to, say, load balance any flow, you had to provide two distinct matches with a separate set of actions to perform. What if I want to match against an IP and load balance it over 2 or 3 or 4 ports? Well, unlucky me. In 1.1 we got port groups introduced that allow you to do that, as well as virtual ports that are basically a representation of a non-existent interface, an interface say to a tunnel, be it encrypted or not, GRE or IPsec. And also we got a support for MPLS tags and multiple VLAN tags. Single VLAN was available in 1.0 but not multiple. The most important feature of 1.1 though has become multiple tables. Unfortunately, this feature, while it remains to be the most desired one, is the least supported. That is because the underlying hardware for a flow table is a TCAM chip, and most vendors do not have devices with multiple TCAM chips. And without that, you can have multiple tables only in software implementation, basically in a very slow one. No production-grade network will ever consider such kind of a device. But nevertheless, the multi-table feature remains to be highly sought after, and hopefully someone will invent a way to implement it in hardware. In 1.2 we got an optional IPv6 support, as well as a way to define multiple controllers for any given switch, so that one of them becomes a backup controller in case of a primary device failure. In 1.3 we got a tunnel ID match field, which allowed us to match against, for example, GRE tunnel ID and provide actions to this particular flow. And since then 1.3 is considered to be the stable OpenFlow version, which is used for all current controller software developers and vendors to develop their features. 1.3 got a lot of iterations, but in the end, we got a new one, OpenFlow 1.4. It isn't considered to be stable yet, and most of the features that it introduces are more of an underlying framework upgrade instead of adding new matches or new actions. But in the end, in 1.4, OpenFlow protocol is very different from OpenFlow 1. Most fields were transformed from a simple enumeration of, well, let's take for example match fields. Match fields were transformed from a simple enumeration of 12 possible fields, one after another, to a TLV structure with type, length, and value elements that basically allow us to extend a number of match fields to indefinite. We can add as many new types with the corresponding length and value entries as we want. Same transformation happened with most of other elements of OpenFlow. Actions, instructions, and many other protocol elements were transformed to a TLV type of structure so that we can extend it later without requiring us to add yet another OpenFlow version and require all switches to upgrade. So that's been a very short tour over OpenFlow protocol and its features. And hopefully it gives you a nice introduction of how the protocol works and its role in SDN. It is quite simple by design, but with future versions we got a lot of features and a lot of functionality to actually make it a decent fit for a management protocol of a real production-grade network. Next, we're going to spend some time reviewing what SDN software is available out on the market and what you actually can download and use to start playing with OpenFlow and SDN in general today. Thank you.